Hello, my name is Carolina Krause, and today I will be talking about collaborative filtering and matrix factorization for recommender systems. This topic is extremely relevant in today's expanding digitized world, where many people use multiple apps that use recommender systems daily. These are just some examples of popular companies that not only use recommender systems, but also the collaborative filtering technique, including Netflix, Amazon, Spotify, YouTube, and many more. This technique is powerful because it elevates user experience by creating personalization and optimizing content discovery, which in turn increases engagement by users. In addition, it helps overcome the information overload problem and promotes data-driven decision-making. Recommender systems are a type of information filtering. There are two main types: content-based filtering and collaborative filtering. There are also hybrid recommendation systems which combine the two methods. As you can see in the figure, collaborative filtering looks at the user-to-user interaction, while content-based filtering looks at the user-to-item interaction. We will be focusing on collaborative filtering for the purpose of this presentation. Collaborative filtering is based on users who have similar past interactions. The key idea here is leveraging the concept of collaboration to produce a new recommendation. These methods have frequently given better performance and accuracy than other recommender system techniques. There are two primary areas of collaborative filtering: neighborhood methods and latent factor methods, which matrix factorization is a part of latent factor methods, which I will go more in depth on shortly. Some other key features of collaborative filtering to keep in mind are that it is not recommended for sparse data, and the quality and quantity of the data is important. In addition, these methods have lesser time consumption and high efficiency. However, they are only for the top end recommendations and not for user rating predictions. In this chart, you can see a breakdown of the collaborative filtering methods and their advantages and disadvantages. There's the memory-based or neighborhood methods, which include user-based and item-based collaborative filtering representative algorithms. While having its advantages, they have their limitations, including being dependent on human ratings, as well as the cold start problem for new users and new items. In addition, they encounter the scarcity problem on the rating matrix and have a limited scalability for large datasets. On the other hand, there are model-based or latent factor methods, which address some of these limitations. Some of the representative algorithms for this kind of collaborative filtering are slope-one collaborative filtering, as well as dimensionality reduction, which includes matrix factorization, such as SVD and PCA, which we will dive into later. These methods address the scarcity and scalability problem and improve prediction performance. Some limitations are that they require expensive model building, and there is a trade-off between the prediction performance and scalability, as well as a loss of information and dimensionality reduction technique. Lastly, there are hybrid techniques, which are a combination of the two, and further overcome limitations such as scarcity and gray sheep, as well as improve prediction performance further. Now, to turn the focus back to collaborative filtering, I will briefly go over the two types mentioned above. There are neighborhood or memory-based methods, which are centered on computing the relationships between items or between users, as can be seen in this Netflix example in the diagram shown. And there are latent factor or model-based methods, which try to explain the ratings by characterizing both items and users on factors inferred from the ratings patterns, say 20 to 100 factors, as can be seen in the diagram. Collaborative filtering techniques are powerful, but they also come with a set of challenges, including data scarcity and the cold start problem, which occurs when a new user or item enters a system, because new items might lack sufficient user interactions, and new users might lack a history of preferences. In addition, these algorithms can face scalability issues when dealing with large data sets or a large number of users and items, especially algorithms like matrix factorization, which is computationally expensive. Another issue they encounter is referred to as gray sheet, which refers to users who have unique preferences and tastes that make it difficult to develop accurate profiles for them, as well as popularity bias, as they tend to recommend popular items more frequently, which can result in a lack of diversity and may not effectively promote lesser known items. Now we will zero in on matrix factorization and all its different flavors and how it works in recommendation systems. It's a general term that includes methods like PCA and SVD. Matrix factorization decomposes the user item interaction matrix into two lower dimensional matrices, as can be seen in the diagram shown. It characterizes both items and users by factors, inferred from item rating patterns. How the correspondence between item and user factors leads to a recommendation. The main idea here is the existence of latent features representing the relationship between items and users, where the interactions can be modeled more effectively, and the ultimate goal is to optimize the loss function. There are many different matrix factorization techniques, but we will only go over 3 of them: singular value decomposition, principal component analysis, and alternating least squares, which have been used more frequently in recommendation systems. There's also stochastic gradient descent, non-negative matrix factorization, probabilistic matrix factorization, tensor deep matrix factorization, factorization machines, and weighted regularization techniques. Singular value decomposition, or SVD for short, is one of the most popular matrix factorization techniques. It identifies latent semantic factors in information retrieval. In the collaborative filtering domain, it requires factoring the user item rating matrix. However, it often raises difficulties due to the high portion of missing values caused by sparseness in the user item matrix. It works by decomposing the user item interaction matrix into 3 matrices: U and the transpose of V, which are orthogonal matrices, and S, which is a diagonal matrix containing singular values, composed of the normalized S values and the magnitude of S values, as can be seen in the equation shown. The latent factors are derived from the singular value matrix. Now we break down the equation for matrix factorization using SVD, shown here. R is a user item interaction matrix with M rows or users and N columns or items. RUI is not shown here, but it is the interaction or rating of user U with item IM. U is a user matrix with M by K dimensions, where K is the number of latent factors, and each row represents a user U. Then we take the transpose of V, which is an item matrix with N by K dimensions, but each row represents an item IM. The multiplication represents the dot product of the user U and the transpose of the item matrix V, and the result is an approximation of the original user item interaction matrix R. The latent factors K are hidden features or characteristics that represent the underlying preferences of users and items. The choice of K determines the dimensionality of the latent space. Principal component analysis, or PCA, is a dimensionality reduction technique that can be viewed as a special case of SVD. The principal components of a dataset can be obtained from singular value vectors of the data matrices SVD to reduce the dimensionality of the user item interaction matrix. The goal is to capture the most significant patterns in the data while reducing the number of latent factors. In combination with matrix factorization, it improves computational efficiency and reduces the impact of noise in the original data. The choice of the reduced dimensionality K is a hyperparameter that needs to be tuned. Next, we will go over the steps for performing PCA. First, we start with the user item interaction matrix R, which can be seen on the left, where each entry RUI represents the interaction or rating of user U and item J. Next, you center the data by subtracting the mean of each row or user from the corresponding row in each column or item from the corresponding column, which ensures that the data is centered around 0. Next, you apply PCA to the centered matrix by first computing the covariance C with the equation seen on the left, and then performing eigen decomposition on covariance matrix C to then order the eigenvectors based on the corresponding eigenvalues in descending order. The next step is selecting the principal components, which is done by choosing the top k eigenvectors, where k is the desired reduced dimensionality, and these represent the most significant directions of variance in the data. Then we project the original centered user item interaction matrix R onto the selected principal components using the first projected matrix equation shown, where Vk is the matrix containing the top k eigenvectors. Now comes the part where we use the projected data for matrix factorization as input and can apply techniques such as SVD or ALS to factorize the reduced dimensionality matrix into user and item matrices U and V transpose using the second projected matrix equation shown. Once these matrices are obtained, you can make recommendations using reduced dimensional representations. The predicted ratings for user U and item I can be calculated by taking the dot product of the corresponding rows in U and V transpose. Next, there is alternating least squares, or ALS for short, which is an optimization algorithm used for matrix factorization. The goal is to decompose a user item matrix into two lower dimension matrices, user matrix U and item matrix V, by minimizing the squared error between the observed and predicted ratings. It alternates between fixing one matrix U or V and optimizing the other and continues until it converges, making it an iterative approach. Here you can see the ALS objective function, where U is a matrix of user factors, V is a matrix of item factors, RUI is the observed rating or interaction for user U and item I, UI is a vector of factors for user U, VI is a vector of factors for item I, and the lambda is the regularization parameter, which helps prevent overfitting by penalizing large values in the user and item matrices. The advantages to using matrix factorization techniques and recommender systems are that they have good scalability with predictive accuracy, they're effective in handling sparsity, and they have flexibility for modeling various real-life situations by incorporating additional information such as implicit feedback, temporal effects, and confidence levels. They can also mitigate the cold start problem and often incorporate regularization terms to control overfitting. These make them superior to classic nearest neighbors techniques for producing product recommendations. But like any approach, it also has its disadvantages, including lack of interpretability, limited handling of temporal dynamics, sensitivity to hyperparameters, and overfitting in small datasets. They also have difficulty handling multiple types of data and capturing complex patterns, leading to a limited diversity in recommendations. There are many other applications of matrix factorization, including image compression, topic modeling, genomic data analysis, face recognition, data denoising, graph embedding, audio source separation, fraud detection, and others. Thank you, and please let me know if you have any questions.